Okay, Edx M3, January 2010, question 1, on variable acceleration, and in this case acceleration is a function of time. Fairly short question, fairly straightforward as well, so long as you can integrate cos. What we've got is a particle of mass 0.5. We'll pause the video and read the question, make sure you're clear what it asks. Right, so m equals 0.5. And when t equals 1, v equals 6, that's going to be important. And we've got the force is 4 plus cos of pi t. Now, that's the force. Let's get the acceleration then. So acceleration is f over m. M is 0.5, so the acceleration is 8 plus 2 cos pi t. Now in this case, the object is moving along the positive x-axis. The force is directed away from the origin. X is measured from the origin. So we've got a setup like this. There's the origin, there's x. The force acts that way. The acceleration which I'm calling x double dot because that's a habit, that's what I tend to write it as on those diagrams. In this problem though, we're going to call the acceleration dv by dt, and because the force is in the direction so as to increase x, in this case the acceleration has a plus sign, so it's dv by dt equals 8 plus 2 cos pi t. And now it's a simple matter of integrating that. So integrating that to get v, we get v equals 8t plus 2 over pi sine pi t. I'll put a bracket on that to avoid any confusion. Obviously, doing it this way, I needed to put a plus c in. I could integrate between limits, but it's just as easy to put a plus c in. Now, we want to find the speed of this particle p when t is 1.5. So first of all, we've got to find c. So let's do that. When t is 1, v is 6. So if you want to pause the video and just have a go yourself, you should get c is minus 2 from that. So check that. And then that gives us this expression for v. 2 over pi sine pi t minus 2. Okay, all we've got to do now is find the speed when t is 1.5. So on the next page, I think I've written down the v again. There it is. T equals 1.5 then. And again, you might like to try this yourself. Putting those values in then, we get 12 minus 2 over pi minus 2, which is 10 minus 2 over pi, which they've got in the mark scheme was the answer, or in decimal form 9.36. That's it, and that's obviously meters per second. Now just one point with this question. Let's go back to the first part of it. We could have done this using an equivalent method that looks slightly different. We could have used the idea of impulse of a variable force and done it as the integral of f dt. That's the impulse of a variable force is the change in momentum. Now if you have a think about it, you'll see that's exactly the same thing as what we've done here. It's only that you're integrating f instead of acceleration. So you've got the masses in there, whereas when you integrate just the acceleration, you've just got v minus u effectively, the difference in the velocities. Okay, so you could have done it that way, that would have worked equally well. Obviously the limits of integration would have been t equals 1 to 1.5. Now as far as the marks are concerned, the mark allocation for this question. We've got a mark for stating the acceleration in the form dv by dt, so b1 there. This is the method that the mark scheme used, but obviously they would have given marks for the impulse method as well. For integrating correctly, M1A1, I'm getting the right terms in this line here with the plus C, and then for finding the plus C, another M1A1 method accuracy marks. So that's 5 marks, 2 marks left on the next page for putting t equals to 1.5 in, and for finding the correct final velocity, another M1A1. And that's it. So thank you for listening. Here's some information about the Further Math Support Program.